Okay, we're back. Some of our remote people are with us, and many have left. Maybe they'll join again, but either way, we will move on, and this will be available later. So I'm going to start a screen share. What we are going to do in this session is, let's get this just set up properly so that the people here and the people at home can see it. Okay, very nice. So what we're going to be doing is we're going to be going through some of like the code. And we'll do a raise of hands quickly. Who wants to see the runtime system high-level overview first, and who wants to go straight into compilation to continue what we were talking about right at the break and shortly thereafter?
I think I will go with
Former? Okay, former it is. So here we are in pyretic core, and we're just going to review our things one more time. So we've got classifier.py. So this is stuff that supports compilation. In fact, the core compilation, the core cross-product portion of the compilation logic is in there. And the definition of the classifier and so forth. Language.py, that's where the language is defined. Language tools.py, that's a bunch of useful stuff for working with the language. Network defines the network, topology, so forth. Packet defines the packet. Structure and some utilities for that. Runtime is the runtime itself, and that's where we're going to be spending the first part of our time now. And util is just a couple of interesting utility things. So let's jump into runtime.py, and we will start scrolling down. So the first thing is, there are a bunch of import statements. So we're going to import utility, we're going to import the language, we're going to import the tools, we're going to import the network, we're going to import the packet. Then we're going to also import a bunch of stuff on multiprocessing, because we do make use of some multiprocessing capabilities in the runtime currently, logging and so forth. So now, let's make sure I can still keep scrolling. We will look at the definition on line 43 of the runtime itself, which is a Python class. Okay, so you create a runtime instance in Pyretic. That's what pyretic.py does. In fact, I'm going to quickly go back to the top-level Pyretic directory and pyretic.py, the script. So if you're using Pyretic, it's all set up? Or
there's like a bowl with a bunch of stuff in it. I don't know if that's the final stuff.
That's probably not the final stuff. Okay. But if you can keep an eye on that. So pyretic.py, if you're a user of Pyretic, this is what you run. So what is this thing? Well, basically, it's a Python script that, does some signal handling and parses out command line arguments and all that wonderful stuff. And in its main, it uses these command line arguments to set a bunch of options, and imports some modules and does some other wonderful stuff. Pre-processing sets recursion limits and other things that involve resources, and sets up a logger. And finally, at line 163, it starts to do something that's truly interesting, or fundamental. Namely, it creates a new instance of the runtime. So it calls the runtime, and it provides a bunch of parameters to the runtime. We'll go through these in the runtimes init again, but I'll quickly give you. We create a backend. We provide a main method, a set of arguments. These are provided by the command line, set of options, and some options about mode and verbosity. Now, we can...
Sure. For a second. I'm looking on the GitHub. Should I be seeing the same line numbers as you?
If you're looking at the master branch on the GitHub,
pyretic.py.
Are you on pyretic.py or?
Yeah, we're on pyretic.py. Right? Yeah. We moved to pyretic.py. Sorry about that. Yeah, so we're in pyretic.py. So pyretic.py, as we told you, we have kind of a layer underneath. Typically, it's POX. It could be another OpenFlow-based thing running. So in pyretic.py, we start both that thing and we start the actual main portion of the Pyretic runtime. So there is an option to be able to go into this mode where you're doing testing and you just run Pyretic in front end and you set up the back end separately. So that's what this whole if not options front end only is about. So in any case, generally you're going to be running not with the front end. So what happens now? Well, what we're going to do is we're going to create we'll basically do a whole bunch of junk that's needed to set up the POX executable running as a normal Python program and sending and hooking up to the various things in the system we want it to hook up into. So we've got these two things now. So the runtime, which we've created as an object, and once it's created, it just starts doing its runtime thing. And then we also may launch the back end, which actually requires a whole bunch more code to get working nicely. And that back end will automatically connect up with the runtime front end. They know where to find each other, and they go ahead and do that. And that's basically what's happening in here. So what it boils down to, most important thing that happens is we create a new instance of the runtime. We feed it the back end. So now that we've covered that, we can now go back into the runtime itself and say, okay, what is creating the runtime involved? So we're back in runtime.py, and we're at line 43. And this describes what the runtime system does briefly. It does packet handling, compilation to OF switches, topology maintenance, blah, 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 blah. It takes a variety of parameters which are actually documented. I know this is much better than previously. Ask a.
So why would you ever want to run a front end?
Well, let's say you were developing a new backend, or you were debugging the connection between the front end and the back end because there was something obscurely weird happening and you wanted to find out where it was happening. Yeah.
I might be just repeating something you just said.
No problem.
I'm just trying to. I'm one file on it. So
no worries.
Basically, you fire up the runtime at one particular it's called the backend, and then you separately fire up a POX executable. And then you're going to use like a Unix domain socket or something between them.
Yep.
Is that how they communicate?
Yeah. So in terms of communication,
Pyretic running and then POX running as a separate executable.
Yeah.
And then now everything's going to.
Yep, exactly. So in terms of how this runs, the question was, how does this all fit together? So POX is going to run as one executable. Pyretic is going to run as another. There's going to be a Unix domain socket that connects the two. They know how to find each other on that socket. They know where that socket is and so forth, and they will connect up. So the Pyretic script, if you're running it like normal, will just launch these two separate processes and let them connect to one another. If you're running front end only, then it's up to you to set up the POX backend running as a separate process. And you would do that for purposes of debugging or development or whatever.
And so is there like a specific format that you follow, like a JSON messaging or something between these two POX? For example, if you want to ship to some other controller or something. Yeah.
So the question is there a format that we follow between these two? JSON, etc. And the short answer is yes, it's ill-documented, but and it's not quite as well structured as it ought to be, but it is JSON based.
Right. And is there like some way, like in the file, that you can see this thing, even if it's not very well?
Oh yeah. And if you want, I can show you where that is right now, or we can move on. Well, yeah. Well, okay. So we're gonna keep going, but we'll come back to this. And yeah, so basically, when we create the init, so the initializing and constructing a runtime object, basically you start off by just creating a whole bunch of stuff. I'm going to highlight some of the most interesting lines in here, and we'll ignore the other ones unless they're questions. So line 62, self.network, we're going to create a new concrete network object. And this concrete network object is going to do a bunch of useful stuff for us. And we'll go into the concrete network object code in a little bit.
So what is the use of concrete? What's the basic use of concrete?
Oh, it's to actually give you access to the mininet topology and network.
Like learning the whole
Yeah, yeah, and interacting with it and so forth. So that's line 62. And line 64 is also another one. It's basically we take the main, which is literally that thing, def main, that you provided to pyretic.py in your file that you provided, def main. This is the main. And so we actually create that thing running with the arguments that you supplied on the command line. So this is now a running process. And it's called self.policy. Let's see, other interesting things. In line 74, there's something called self.dynamic_subpolicies. This is an important thing. This is, so let's say I have a dynamic policy. That's the thing I return to my main. And that dynamic changing policy includes many other smaller dynamic changing policies in it. And as that top-level dynamic policy evolves, some of them it gets rid of, and it also creates new dynamic sub-policies that it then adds, right? So you've got one big dynamic thing that has lots of smaller dynamic things, some of which may be arriving and disappearing. What we don't want to have happen is we don't want to have every dynamic sub-policy that has ever existed continuing to use processor space and continuing to receive packets and continuing to potentially do stuff, including muck around with data structures that are in the runtime. So what this variable does, and it's a very important thing, is it tracks what the current set of dynamic policies that are active on the runtime are. And these are the only policies that will have any effect on the runtime.
That's line 74.
That's line 74. And on line 75, we call our first call of the function dynamic update dynamic subpols, which is a function that does what its name says. It's going to analyze the current policy compared with the last policy known. It's going to figure out what the differential, if any, in dynamic subpolicies is, whether there were new dynamic subpolicies that were added or subtracted at anywhere in the syntax tree. And then it will set that as the new value of dynamic underscore subpolicies. Okay? And we're going to see that logic in a little bit. So other things that are, so there's some, network policy triggers and so forth, but we'll get to those a little bit later. There's some old rules, new rules. Yeah, the rest of this you don't. I'll just point out line 82, self.manager manager. So this is something that's used between multiple Python processes, subprocesses, to communicate with one another in a thread-safe way. And so we'll make reference to that, possibly in the code, depending how deep we get. So then on line 100, we're going to see what's the first thing in the runtime. It's the packet interpreter. Okay, so this handles packet events. So if a packet comes in to the runtime, this is where that packet goes. And we're going to go through this logic step by step and make sure you're super clear on it. So line 100, we see it takes a concrete packet. So this is actually a packet that's in the form of a Python dictionary. So it's been marshaled somewhat from the wire, but it's still rough. It doesn't necessarily contain all of the metadata we want.
Where's it coming from?
Actually, it does contain, so
Pox gives this to you?
yeah, so Pox hands it to the pyretic backend over the Unix socket, and then the pyretic backend code calls this code in the runtime.
Shabazz asked this question.
Sure.
When you pass it over the Unix domain socket, it's serialized?
Yeah, it's JSON, it's serialized, it's, yeah. Right now, I'm not very happy with that code. We rely on a Python library. In part, we rely on a Python library called async chat, which has many bugs. several of which are undocumented. Yeah, we've patched it multiple times, and it still doesn't work the way it ought to. So that would motivate the move to Thrift or something like that as a short-term fix, or owning the whole stack as potentially a longer-term fix. We might spend some time hacking on that, later today or Friday, or maybe not. Okay, so we get this concrete packet. So first thing we're going to do is we're going to grab the policy lock. And the reason why we grab this lock is because we don't want the policy changing in the middle of our interpreting a packet. That would be bad. It would give us some weird, inconsistent thing. You could imagine the policies forward 1 at one moment and forward 2 in the next change. And if we're evaluating while that changes, there are a whole variety of errors, including potentially memory accesses, which are incorrect, and all sorts of terrible stuff that can arise. So this is a point of serialization of the code. Whenever we evaluate a packet, we hold the policy steady. We don't allow it to change. And we create a pyretic packet on line 108 by using the self-concrete to pyretic packet method. And you can take a look at that. It's not super interesting, but it gets things exactly into the pyretic packet form, which is essentially a dictionary with some other useful features. The next thing we do is on line 111. We go and we take a look at our policy with respect to this packet, and we find out, will any queries be triggered by this packet? And we get that whole set of queries. This is information that's important for a variety of reasons later. So we get all of the set of queries, all the buckets, forward buckets or count buckets that our packet might hit, and we store that. Then we do an evaluation of the policy on line 114. So basically, we take our pyretic packet and we put it into the policy, self.policy.eval. And you'll see, we'll go into the language in a little bit, but basically every primitive policy has an eval and every combinator has an eval, just like they all have compile, which allows them to produce a classifier. They also have eval that are defined. So we're literally just doing the eval. This goes through the syntax tree and evals at every point appropriately in there and outputs some set of packets, possibly empty. And that is our output, and we store that. Now, what we do is only after we've evaluated the policy fully, we don't want any side effects occurring while we evaluate the policy, so we don't want evaluation to accidentally change the policy or anything like that. So while we're evaluating, packets may go into buckets, but nothing, no queries will call back, no changes will be triggered to the policy. Because otherwise, if that were to happen, well, we could run into a variety of issues. So what do? We wait until we've gotten our output. Once we have our output, what we'll do is if we'll set a variable, not as important. What we'll do is for each query in the queries, what we're going to do is we're going to apply that query to the contents of its bucket. So basically, if you've registered any callbacks, so forth, at this point, we're going to be, sending those back to their handling routines, the callbacks, and possibly updating or changing things about the policy. Now, at line 123, what we're going to say is, hey, if the buckets triggered any of these kind of updates or changes that are now pending. So when we do changes to policies in 2 phases. What are we going to do? We're going to update the set of dynamic subpolicies. So that way we're working with the right set of dynamic subpolicies. And we're going to update the switch classifiers. So we're going to do proactive recompilation. Question?
Yeah, so what the self.in bucket applied on 117 and 120,
yep.
Is that looked at by some other module? Because I don't see what it's doing here. It's just like in the
Yeah. So we'll see later. Well, actually, I'll just do a find. See if I can find that for you right now. So in bucket, there we go. Okay, so basically, a policy change could be driven by any one of the buckets updating itself. But what we wouldn't like to do for efficiency's sake is have several changes occur from several buckets and have the policy recompiled for each one and reinstalled for each one. So what we have here is a flag that lets us know, hey, we're in the middle of a bunch of changes which are potentially triggered by buckets. So we're not going to do that. And instead, what we will do in the packet handler is, if the query changed the policy, so if on line 123 we evaluate self.bucket_triggered policy update, so if that has been set to true by any one of the queries or by all of them, at that point, only then will we update the dynamic sub-policies and do the update to the switch classifiers, which does a full recompilation phase and install. And then finally, we'll set self-bucket_triggered policy update to false. So we don't do that in the next round of compilation. Finally, we take, yeah?
This is probably another dumb question. But like
No, there are no dumb questions.
There's no notion of like concurrency or threading as part of the control. I guess packets can. I'm just wondering.
Yeah. So
I noticed you didn't use a lock there. So it's just,
well, so everything here is wrapped up in the policy lock. So you can't change the policy. You also can't start another packet evaluation until you've let policy lock go.
So you can only, you basically evaluate one packet at a time. Is that...
Yeah. When we're interpreting, we evaluate one packet at a time, and we only allow the policy to change in between packet evaluations.
Yeah, okay.
Or to finalize. So there are a variety of little bits in the code that kind of ensure this. And it may not be the most elegant structure. I'm definitely open to, definitely bug anyone who wants to bang on it and see if they can create, some kind of race condition that I haven't anticipated, or they think, they've got a better way. Like that's awesome. I would love to see that. But for right now, on line 129, we take the output, we turn it into concrete output, and then we just send the packet out. And the last line in here you can ignore because the reactive, this reactive zero mode is probably going away in the next release anyway. And it's kind of confusing. So to go through the interpreter, what does the interpreter do? It grabs a lock. It turns the concrete packet into a pyretic packet. It finds all the queries that will be affected by the evaluation of this packet, if any. It evaluates the packet and produces the output, which it holds. It then checks and says, hey, if I did have any queries whose evaluation would be affected, who would be evaluated in this packet, let me evaluate all of them, make sure I don't update until I finish doing that. And then if any of the packets that have gone into these buckets have triggered changes to the policy, I will then update the policy. After that's all done, I will release the lock, allowing the policy to change for other reasons, say a topology change, or other packets to come in and be evaluated. And with a little bit of parallelization here, I will send my output out into the network. And that is what the interpreter loop does. Are there any questions about that? Okay, great. So since we've gone through that, we can now look at the dynamics code. We'll go over this briefly. We'll see how much detail we go into based on your questions. So the first thing in here is on line 142, handling policy changes. Okay, so as it says in the documentation, it updates the runtime behavior, both the interpreter and the classifiers, if some sub-policy is going to be changing. So again, since this is a policy change, we grab the policy lock. Then what we do is we do a traversal over the policy on line 150, 151, in which we determine, okay, which portion of the policy tree has changed? Because maybe only one branch of it's been invalidated. Maybe the rest of it is just fine. So this is a little bit of sort of dynamic recompilation here, where we're going to try not to recalculate things that we don't need to recalculate. And so we're going to mark those portions of the policy tree that are no longer good as being stale or invalid or whatever. And that's what we do over here. Then on 154, we check, hey, is this a network update? So did the network topology change and cause this update to be triggered? If so, we'll flag it accordingly. If yep. Oh, sorry about that. If otherwise, perhaps it was driven by the application of a bucket. You know, packet goes into a bucket and that causes some change. Okay, then we're going to set bucket underscore triggered update that we used before. Otherwise, it's not a network change, and network changes can affect multiple policies at once. It's not a bucket change, of which there might be multiple such changes at once. So we're going to assume if it's neither of those, it's a unary change, a change which just happened in isolation by itself. Now it's possible we could be hooked up to an external event source such that there are events that are co-created. Right now we don't have the mechanism in the runtime system for recognizing that, so we can't deploy this optimization, which is an optimization that avoids recompilation until we're sure a set of changes is finished. So in this case, since we can't apply the optimization, this last else on line 162, then we do update dynamic subpolicies and update switch classifiers. Now, if this was a network change, on the other hand, right, we would have hit the first if and just set a flag instead of doing any recompilation. So let's take a look at what happens here. So we grab the lock. We did some tests to see, did the network topology actually change, or is this a false alarm? We make a copy, we grab the policy lock, then we're going to look at the various dynamic subpolicies that are, so every dynamic subpolicy, as we were discussing in the last section, is sensitive to network. They all have a set network method. So this is where we update them. So for each one of these policies and dynamic subpolicies on line 184, we're going to call on line 185 policy.setNetwork self.network. And they'll be notified, hey, there's a new network here. If there's anything you need to do, print out, change, whatever, do it. And then, finally, after all such dynamically changing policies have been changed, and note each time one of them, if I call set network and it actually causes the policy's behavior to change and the output to change, then it's going to go up into handle policy change because that portion of the policy now changed. But we're not going to recompile because it's a network change, and instead we'll wait till all of those are done, and then on line 192 we'll do the update dynamic subpolicies and the update switch classifier again, and we'll unset our flag. Likewise, what we already saw in the interpreter loop, how that same kind of logic plays out for query-induced changes. So update switch classifiers, what happens here? Well, this is line 199. Basically, you can ignore everything except the proactive mode lines, 208 and below, and basically we get a classifier by calling self.policy.compile. So that's step one. We get our classifier, and step two on line 215 is we install that classifier.
Does that mean like send row table modifications?
Yep. Yep, that's exactly what self.install classifier means. And so self.policy.compile is that whole compilation process we were talking about. And there's another phase to compilation. So self.install classifier doesn't just send stuff straight down to the switch. And we'll go through, there's a whole bunch of additional compilation-based logic there. But the cross-producting occurs in compile. Okay, so cross-product in line 209, another pass and actually pushing stuff down to the switches on line 215. So before we get to the compilation code, let's just take a quick look at what updating dynamic subpolicies does on line 218. So basically what we're going to do here is we're going to first take our current set of dynamic subpolicies and we're going to copy them to a set of old ones so we can take a look at the difference. Then we're going to basically do an abstract syntax tree fold, and this is provided in language_tools over the entire policy, in which we're going to take this new change self.policy and we're going to add every single dynamic subpolicy that exists in it into a set, which we're then going to return. Then we will look in the differences between old and current and essentially detach any of those subpolicies which were previously attached, previously running, but no longer effective in the current policy, so we threw them out. So we're going to now detach them, which effectively keeps them from getting any new information and doing any additional processing. And likewise, anything that's been added, any new dynamic subpolicies that I've added will attach. So they'll receive set_network events, they'll receive packets if they're supposed to be getting packets, etc. So that is sort of the structure of the runtime in terms of its high level, keeping track of stuff, doing packet interpretation, and changing over time. Any questions about that before we move on to looking at how compilation works? Yeah?
I actually have a lot of
Okay, go for it.
This last method here. So,
Sure.
So
Let's
first
dig
of all,
in.
a subpolicy is just like something that's composed with other subpolicies to make the actual policy.
Yeah.
Is that what a subpolicy is?
So actually, probably a good way to do this is, maybe I can draw something. I'll describe it with my hands right now. So like, let's say I have a policy that takes, so I have a load balancer whose behavior changes over time, right? I have a MAC learner whose behavior changes over time. I sequentially compose them together to get a new top-level policy, okay? So this top-level policy happens to be static because I just did sequential composition, but you could imagine that maybe it's a dynamic policy that takes these two things and combines them in different ways at different times. But either way, that top-level policy has many sub-policies because both the MAC learner code and the load balancer could break up into lots and lots of little things inside. But those two things are both sub-policies which are dynamic. And in fact, the MAC learner is built using flood, which is also a dynamic policy. So MAC learner has another dynamic sub-policy in there called flood. So of our top-level policy, we've got two direct descendants who are sub-policies that are dynamic, and someone very further out, flood, that's a sub-policy of MAC learner, and therefore of the top-level policy as well. So when I did the traversal, I would get these three policy ID numbers, or policy ID objects references.
Okay, so now this function, you are basically, okay, so for the particular policy that you're basically figure out certain things that we have a chain.
Yeah, well, no. So here's the deal. When I update self.policy, it changes in some way. We don't know what way that was. Right? So what we do is the last version of self.policy, we had created this data structure that had all of the dynamic subpolicies in it. Right? Then when we recompile, it's going to have new stuff. So what we do is we take our old data structure that had tracked the subpolicy references, copy it over to an old one. Then we retraverse it to find what are the current dynamic subpolicies. We collect those as a set. We compare the two, the old and the new. So the fold detects, and then the set difference on either side figures out what's been removed and what's been added. And
now what is attached?
Yeah. So basically, high level, and we can dig into the code more later. But high level attach says whenever a set network occurs, make sure this thing gets the set network. And maybe some other very esoteric stuff, but I'm not even sure in this version of the code if that needs to be there.
Oh, I see what you mean. So the stuff that's added, you would offset that.
Yeah.
The stuff
Exactly.
That's removed, you basically remove it from that.
Yeah, and so there might be some corner cases where it's not just set network that might be getting fed to the objects, but something else. So you wanna make sure that they can't affect things. But like if you look in handle network change, right? We have a handle network change event that occurs in the runtime. How does it inform the dynamic policies? That's line 185 for each policy and dynamic subpolicies, whole set network. But only on those that are currently in dynamic subpolicies. And the attach and detach act as an additional safety feature. I think it's necessary, but it's kind of like to cover a corner case. We can dig into the code later. It's probably not important for right now.
This might be what you just said is important, but how attach and detach are related to the set of that dynamic subpolicies. Is that what you just said? Is not.
Yeah. I was saying that's not super important, but you know what? Since it came up, let's just take a quick look at it, and we'll see if I documented things nicely. Yeah, there we go. Dynamic policy. Okay, I think I remember what's going on over here. So every dynamic policy also has self.notify, which is not well defined over here. I mean, it's not described in the documentation, and I should change that. But basically, this self.notify does something very interesting. Basically, what it does is it says, if I've changed, so if my changed method is called, then if I have a self.notify, I'm going to call that self.notify back with myself. Or, in other words, if there's some entity that's interested in my changes and might be changing based on my changes, or might be updating some metadata or doing some other thing each time I change, then I need to let that thing know that I changed. And that thing generally is the runtime. So this provides the method whereby dynamic policies the runtime can let the dynamic policies do stuff by just going through the current dynamic subpolicies. But if I'm a dynamic policy and I've changed for some other reason, maybe because I was accepting keyboard input or something, how does the runtime find out about that? Is it going to poll me continuously? No. What I'm going to do is I'm going to provide, the runtime system is going to provide a hook to itself that's going to be stored in the self.notify. And whenever the dynamic policy changes, it will automatically call this changed method, which will then, if there's a notify in it, call the notify back. And generally that notify only goes to the runtime. Although you can imagine maybe a corner case where you might want to do something fancy that's different. And so just to give you a little more on how dynamic policies work, where is this change set? Well, self.policy. So when you have a derived policy is a policy that has a policy inside it. And so if underscore is a derived policy that has inside it basically this parallel composition of sequential compositions, like we saw before. Dynamic policy is also a derived policy, but it's one whose internal policy changes over time. And so here we see in line 107 that the policy property just returns self.underscore policy. So this is an internal semi-hidden variable. And when we want to set the attribute, so if I say self.policy equals 2, or plus equals 2, or some other assignment in Python, then line 1071 will get called. And what will happen? Well, I'll store the previous policy. I'll update self.underscore policy equal to the new thing that's being assigned. And then I will call self.changed. And you can imagine for some optimizations, it might be useful to know for the runtime to know what the previous value of the policy was, instead of having to figure out what it was. And so you could imagine providing the previous policy value as input to self.changed. But this current version of the code doesn't, because we don't implement those kind of optimizations right now. Does that give you an understanding of how this all fits together? So,
Well, I guess kind of another question is, like, back in runtime.py, in the update dynamic subpolicies, so you do like set subtraction.
yep.
But wouldn't, is it like, where do you don't actually call that update the set, like, shouldn't, yeah.
Okay, so I will go over that one more time in a sec and hopefully clarify. No, don't apologize at all. It's great questions. But I just want to make one. I just want to clarify, or not. I want to reemphasize one point. So the way the runtime knows about the dynamic subpolicies that are currently in operation is through self.dynamic_sub_policies. The way the dynamic policies that are currently in effect know about the runtime is through self.notify. Okay? And self.notify is updated by the attach and detach methods. So when I attach, I literally give the dynamic policy a way of communicating to the runtime. And when I detach, I literally take that means away from it. So it no longer, when I detach, it no longer has self.notify, so it doesn't have a connection to the runtime. So if it does something, it changes in some way, it has no one to tell, and it won't tell anyone. It won't do anything further. Whereas if I attach it and self.notify set, that self.notify is just a reference to the runtime. And so if it changes, it then automatically, each time self.changed is called, will call self.notify. That hook to the runtime that then gives the runtime information that there has been a change. Okay? So when we go back to the previous file, yeah? Too fast?
No, I'm hanging up a little bit on decorator things.
Oh, decorator things, yeah.
Because when you're describing this policy function, assigning.
Yeah. Okay, so
I'm just trying to figure out what this thing is.
Yeah, so this is some Python crap. In line 1066, the property decorator is a decorator defined by Python that says, whatever the name of the thing that's being defined here is, we're going to make that the variable of this class. So if I say, property def policy self, then I basically created or overridden self.policy. If I were to say property def, height self, then I'm overriding self.height as the property. So normally, as the variable. So when I access this, what appears to be a member variable called height, instead of actually corresponding to a real variable like self.notify or self._policy here, what it actually does is it calls this method for access. There are three methods. There's a method for access, a method for assignment, and there's a method for deletion.
Yeah. So if this is like a right-hand side or something, it's going to be property. The left-hand side.
So basically, if I call it property, then I've declared it as a property, and whenever I try to access that value, it does what this function does, and returns this function's output.
If you ever try to set it, it's going to do this.
And policy.setter is exactly, and because I've declared it the same name, policy, it knows it's doing the policy variable. So it's just Python.
Policy.setter doesn't sound like a Python thing. That sounds like something.
No, it's super Python. I mean, it's just the way Python. It's
basically, instead of having to say like basically you can refer to self.policy outside, instead of having to call it like self._policy, which is supposed to be like the private variable, and instead of having to say self.policy open parens, close parens. Like it's all syntactic sugar, right?
Not really.
Okay.
because let's say you said self.policy, open parens, close parens, equals to 5.
Right, yeah.
That would break really bad. You could write a new method called, self.policy underscore set open parens value close parens. You could do that, but that would be uglier. So this is what Python provides you as its general purpose mechanism for doing this kind of stuff, as opposed to ad hocing it yourself. More questions about this stuff? And part of what pyretic's trying to do is hide all this gumbo jumbo from the user, right? So like you just write a dynamic policy and it changes over time, and like you don't have to worry about any of this. The runtime knows that it's changed, and it like updates everything for you, the interpreter and the compilation. It reports the changes to the runtime. The runtime sees what else has changed and detaches the things that should get detached and does all the bookkeeping. Like that's the magic of it, And now we're seeing the dirty, well, maybe not dirty, but we're seeing the, like all the gears and pulleys that actually let you like do self.policy equals new thing and have the runtime's behavior just auto-magically update based on that. You should not override this unless you really know what you're doing. Yeah.
So it is
I mean,
possible to override it, just include the decorator.
Yeah. I mean, Python. The thing is, like, there's not really like private, public. It doesn't provide those kind of mechanisms. So it just provides kind of. Yeah. So if you want to muck with it, you can totally muck with the runtime, but you'll be mucking with the runtime. And you can muck with the language, but you'll be mucking with the language. So you'll be no longer using pyretic, you'll be using some kind of new variant of it that you've created, whose behavior is not necessarily well understood by anyone. That might be what you're looking for. I mean, I've definitely been looking for it many times, but and that's part of what this is all about, is giving you this kind of deep understanding of like where you can, how it all works, so you can, change it if you want to, or work with insight based into the mechanisms if you don't. So now that we've taken a little foray there, let's go back into the runtime. And I'll show you a bit about how compilation really works, and then we'll take a lunch break. Sounds good? Are we good to go a little more? Do we need? Oh, and also. Just
once we're back in the runtime.
Yeah, we're gonna go through your question totally. Yeah, we're going there right now. So here we are at update dynamic subpolicies, right? And you wanted to understand this code a bit better. It was a little.
Yeah. So 227.
227. Yep.
So why this to me seems like it's doing exactly that.
Oh, from the previous one?
Like
yeah, so
you have that function that's like update that dynamic subpolicies variable, but you're not using it, you're just like subtracting out the old ones.
Yeah, so here's the deal. So we're doing two asymmetric set differences. We have our old set of dynamic subpolicies and our new set of dynamic subpolicies. So we're going to first take the asymmetric difference, those things which were in the old policy but are not in the new policy. That stuff needs to be detached, right? Because we don't want it mucking with the runtime. So that's what the first several lines, 225 and 226 are. So for everything in that asymmetric set difference, those things which are no longer hanging around but were around, we're going to detach them. Now, the following 3 lines, what we're going to do is we're taking the asymmetric set difference between what we have now and what we had in the past. So those things which have been added, those things which weren't there before. And those things, well, they need to have 2 things done to them instead of 1. They need to be attached, but they also need to be initialized, because they need to be attached to the runtime, but they also need to be initialized with the current network topology. So first we set their network, and then we attach them to the runtime. And that's what happens. Cool. So,
Sorry.
oh, no worries.
When do they actually get added to that set that you talked
Ah, they've already been added,
about?
right? So when we call update dynamic sub-policies, oh, sorry. Yeah, my bad. They've already been added in line 224. So self.dynamic sub-policies equals AST fold.
Yeah. Okay.
Yeah. And so AST fold is just a helper that's provided in language underscore tools that literally goes across the whole syntax tree, and then at each node, more or less, does whatever the method that's given to it. In this case, we give it an add dynamic underscore sub-policies. And guess what? That checks if something's dynamic or not. And if it is, returns it. If it's not, returns nothing. And so we get a set of those out. Any other questions before I kind of move on to compilation? Okay, so for compilation, as we'll recall, there are basically two phases. There's actual compilation or production of the classifier. That's line 209. And then there's line 215 that does classifier installation, whatever that is. So let's look at the compile first. Okay, so basically a classifier is something which is a bunch of table entries, which we call rules. Question. This is classifier.py. Yeah. So basically a rule just contains a match and a bunch of actions. That's it. And a classifier, more or less, contains a bunch of rules in order. And there are various evaluation methods and other sorts of stuff. But when you boil it down, that's what's going on in here. So now we're going to pop out a classifier for a second to look in language. And what you'll see in language is that each one of our basic things has a compile method. Yep.
Still giving you on.
What? Oh, stretching. Sorry about that. So every policy has a compile that produces its classifier.
So the AST graph that you showed in the presentation, where you showed like this is the piece which makes this table.
Yep.
So this is the thing that will actually make that.
Yep.
Okay.
And also this is the thing that makes things in the middle too.
Oh, okay.
And you'll see how that works shortly. So basically we have some caching code in here, and basically the way the caching works is, hey, if we've already compiled this result and it's fresh, we don't recompile.
Sort of like memoization.
What?
Memoization.
Yeah, exactly. So it's sort of. It's something, and you can look through the exact details of how it works, and we can go over that later, but it's not critical for right now, so I'm going to ask you to ignore that code and just focus on, oh, and also note that each has an eval.
Eval is for the interpretation.
Exactly, you got it. So now let's look at a couple of our most basic policies, like identity. So identity, when evaluated in the packet, returns, well, the set containing the packet.
Well, what is the singleton class?
And the singleton class are those items which there can only be one of. So, like, whereas I might have two different, like I could, I can create two different query buckets, right? So I can say query bucket, another query bucket. And they're fundamentally different things.
Nice.
I also have parameterizable classes, like I have a modify, right? Modify f equals v. I might use a different f, I might use a different v each time. But with identity, there are no parameters involved, and its behavior is exactly the same every time. So that's a singleton. So identity and drop are singletons. There's only one instance of each that ever should exist, right? Whereas you can have many forward buckets, and you can have many different types of matches.
So the memory object that you make is actually the same.
Exactly. Yeah, every identity is exactly the same as every other identity. So it allows you to write identity without having to use the constructor. It basically says this is a class of which there can only be one instance. Oh, and so
Is that enforced?
that is enforced. That is enforced. That is definitional using the singleton thingy decorator. So also all singletons happen to have a very clear classifier, which is basically their identity and themselves. The set containing themselves. That is their classifier.
Does this relate to like drop as well? Like drop
Yep.
is the identity?
Yep. Drop is the thing that matches. So identity is like star, basically, right?
Oh, okay. All right. So it's like a
Yeah, exactly.
regular expression.
Yeah, yeah. So this is a standard for a regular expression. Really, I probably should have implemented all of the OpenFlow bit match language and defined a rule as being something that pairs an OpenFlow bit match with, and I should have defined a subset of the pyretic syntax, which is allowable, but I just didn't because I was lazy. So you know, identity and drop are going to have very simple classifiers and sets and so forth. Return controller also is a singleton, right? Right now there's only one controller in the network. There might eventually that might no longer be a singleton. Now let's look at something more complicated like match. So a match takes some f's that are equal to some v's. So you know, we unwrap all that stuff, and then we have an evaluator which basically looks, you know, at each thing in the map and tests, hey, do we have a match? And you know, if it's not matching, we return set, or if it doesn't seem to exist, we return set. Otherwise, we return match. The classifier over here, two roles: one that matches what the match matches, and returns the identity. So lets it go through. So that's like, you know, itself an ID. And the second role is everything else, you know, goes and does a drop.
What does return set mean?
Oh, this creates the empty set.
Okay, thanks.
Yeah.
Back up the singleton.
What? Mhm.
Are there actually like two notions of singleton? Like the decorator singleton is a Python thing, and your class, capital S singleton, is just a class that you happen to call the same thing?
Yeah. So a singleton is a particular type of filter. So this is just kind of to take some boilerplate out of the drop-in identity.
Right, but then when you have that
The decorator is in no way semantically related to, or rather, the syntax. Like they're totally different things.
Like you could have named like your
Yeah, I could have named it
class-
foobar.
Okay.
I could have named this class over here class foobar.
So the decorator singleton is what Python enforces as there can be only one.
Yeah, so I forget if we're using Python's singleton or if we're using our own, but there's a singleton method that's either defined in Python or in util.py in core.
It's not defined.
But it's not defined here.
Capital S singleton
It's not, yep,
actually is not
totally different thing.
different.
Totally different thing. Okay, great. So let's move on. So we've done so you can see kind of how this, you know, this match relates to the previous matches we discussed, and so forth in the language. You have lots of these different, you know, classifiers that get generated, and eval methods, and we can go through this in depth some other time. But right now, what I want to do is just get the high end so we can go through compilation, which is, so if you notice. Yeah, things get pretty complicated in the count bucket because we've got a whole bunch of stuff in here which, you know, deals with updates and with pulling statistics and with, you know, flow stats replies and flow stats removals message and all these kind of things. But now let's go to parallel. And what we'll note about parallel is, okay, if we look at its evaluation, how does it evaluate? Well, for each policy in self.policies, so each of its operands, it's going to evaluate that policy and then take the set union of the output, which is exactly its definition. Okay, so this is how we do it in a imperative way. There's also a generate classifier. And basically, if we have no policies, well, we're, you know, that's the same as dropping if we're combining nothing with nothing. Otherwise, what we do is we map compile over each of the internal policies. So if I say policy 1 plus policy 2. That creates a parallel policy with pol 1 and pol 2 in a list called self.policies. And what we're going to do is we're just going to get the classifiers for each policy. And then we're going to use an accumulator function that basically takes each one of these classifiers and adds them to the one previous. And this addition over here is addition on classifiers. So that's defined in classifier.pot. That's the logic of the cross product. And we'll see the definition of that plus on classifiers shortly.
And that differs for sequential and parallel.
So we'll see that in a sec. Yeah, it differs from sequential and parallel. So union is just a special type of parallel.
Okay.
That's it. It's just a typing thing. Sequential, again, if we look at
Can you elaborate on that? Because I know that was one thing.
which thing?
You said union is a special type of parallel. Like,
Yeah.
For example, like you can't negate.
You can't negate parallels, but you can negate unions.
So can you explain here now why that's the case? Like, I mean, in terms of like what we're looking at.
Oh, when you say why that's the case, you mean how this affects that?
I'm just curious
How that
when you
makes
said
that
like
happen?
one is like union is a special version of parallel. I'm just kind of like trying to get like.
Yeah,
How
so-
the difference-
Yeah, so union is literally a parallel that's also a filter. So it's descended from both. So it has the filter methods and it has the union methods. It has the parallel methods. Parallel has no negation operator. It is literally
This is
undefined.
multiple inheritance.
Yeah, this is multiple inheritance.
And then what can a union? So you can negate a union, but like are there other things you can do to a union?
No, it's just negate. Well, you can OR it. You can't OR a parallel. You can only sequentially compose a parallel. Sorry, you can only parallel compose.
So why do you have both? I mean, why don't you just have union?
Yeah. So
Also does parallel stuff.
well, no,
Is it a type issue, or-
well, it's a typing. It's definitely a typing issue. So, for example, if I can do match union match, the union of two matches, but I can't do match union forward two.
Yeah. That's,
Whereas I can do in parallel match in parallel with forward two. That's sensible.
union is only applied on matches in layman's sense.
Yeah.
Okay.
Yeah, matches or unions of matches or sequential compositions of, or sorry, unions of matches or
Makes sense.
intersections of
It makes
matches.
sense to take a union of a filter and of an action or something.
Exactly.
Take a
Exactly.
union of multiple filters.
Yeah. Now it's possible you could say write a runtime system that would always be able to figure out what the type of the policy is,
And then just do the right thing.
and then just do the right thing. But that's complicated. That's complex because of all of the. You'd have to look at the netcat paper and look at all of the
Because
transformation
it's like
rules, and
type inference or something.
yeah, and it might be MP complete. It might not be. I don't know. It's not something I bother with. Yeah, not work. It is NOP or something. Not a something. Not a problem. I don't know. Whatever. Anyway, I was trying to make a joke. I didn't manage it. Yeah, you can't.
It happens a lot. I actually made a mistake as well.
Yeah.
The symbol is different for you, right? Like
Hmm?
plus is for, not for unions, plus is for,
Plus is for parallel.
yeah.
Bar is for union.
Oh,
Yeah. So and that's what keeps you type safe. So we put a little bit more burden on the programmer.
But is it correct to say that like anywhere where I had a parallel composition, I could just like apply union and do the same thing? Or is that actually
Anywhere where you were parallel composing filters, it would do the same
Right,
thing.
right.
If you try to do it with non-filters, boom, you know.
Anywhere that you have a union, you could replace it with clause.
Yep.
Not quite, because if
Well-
you've got a logical operator outside.
Well, yeah, if you have a negation outside, well, you can do the replacement. The replacement is not what's going to cause the error, but you might get an
Whatever you
error.
apply to the result
Yeah.
might actually.
Yeah.
Right.
Yeah. So, okay, great. That was a really good question and clarification. So let's just take a look at sequential very quickly. So how does sequential evaluation work? Well, we start off with saying the previous output is whatever we received. Good. That's our input packet. And or rather, the prev output is whatever we received. And in each cycle, and then we set up our output to be our previous output. So if nothing ends up happening, then we're just going to output what we got. Otherwise, for each policy and policies in order, we are going to you know, with some optimizations for recognizing identities and drops, basically what we're going to do is we're going to start off by saying, hey, the output is currently nothing. And then for each packet in the previous output, we are going to evaluate that packet on this policy and add that to the current output, right? So this is that union of a thing that you saw on the slide way back when. So basically we're going to say we got a whole bunch of packets. These were the previous output. For each one of these, we're going to evaluate it on the policy and get that whole set of packets. And we're going to smash all of those sets together. And that's going to be our new output for the next cycle. And then we're going to go back and do that again until we run out of policies in sequential composition. And that's it. And then we'll return the output. So that's exactly how sequential composition works. And when you look at the classifier, it's pretty much the exact same structure as the parallel composition classifier over here. So again, we're going to do a map of the compile method over each of the sub-policies. And then, after doing a little assertion, we're going to do that same reduction, where we basically take the first one, sequentially compose it with the second, then take that and sequentially compose it with the third, and take that, and so on until we're done. And that sequential composition is the sequential composition defined on classifiers. So again, this is what's going to do that other type of cross product. And we'll go look at that code right now.
So basically, when you ultimately compute the cross products, you need to do this with each individual policy. You're going to get basically these things, and then you're going to do like unions and intersections on these.
Yep, yeah, that's right. And actually, so there are a variety of optimizations you could potentially do. Like if you knew this was a long list, for example, what you could do is you could, you know, say break it into segments, sequentially compile each segment, and then smash the two together, so that way you wouldn't end up with one big one and little small ones being added to it. You know, maybe that's more efficient, maybe it's not. But this is an easy and correct way of doing it. So we're going to hop over. Is there a question before? Yeah.
So in eval, when you said previous output, with what I'm having trouble understanding, kind of getting an example in my head of how you would have multiple policies, self-up policies.
No, you only have one self-up policies. But here, let me just, I'll just draw it on the board very quickly. I'm sorry for those at home, you're not going to get to be able to see this part. Thanks, Jen. Okay, by default, when I use operators, like this A plus B example over here, what am I going to get? I'm going to get a new sequential policy. We'll just call it set. And inside this policy, I'm going to have self.policies. And this data structure is literally going to have a list that's going to contain A and B. Okay? Make sense?
Is the list ordered?
The list is ordered. Yeah, lists by definition are ordered. Sets are on is Python's convention. Yeah?
And the bigger policy is?
The bigger policy is this thing, sequential. What I call C, we can call it S, if that's easier.
Yeah, okay.
Yeah.
Yeah.
So this thing is literally a sequential policy, an instance of sequential, whose self.policies contains list A, comma B.
Okay.
Yeah, so then what I do is I do, you know, a.eval the input packet P. And that gives me a set of P prime.
Right, and that's why you send those packets back through.
And then, and I keep doing that because I could. So when I use the operator by default, it just creates a 2-1. But I could say, you know, take this, right? And we'll this will do is it'll create one sequential and then it'll create a second, but I could flatten those into just one single sequential that has 3 members and make my tree shallower, which is one trick you can use to improve compilation time or interpretation, etc. Does that make sense?
Yeah.
Question?
This question might drag us away, of course, but I just want to like put a placeholder in maybe tomorrow. So I was thinking back to your previous discussion about time with the dynamic updates of some policies.
Yeah.
And how you call this thing when the network changes or when policy changes. Update network policy.
Yep.
So this question relates to like the net assay extensions. So one thing. So I notice what you don't have is like update a policy when the value of a virtual header changes. You assume that like the value of a query.
Value of a virtual header changes.
Let me explain what I have in mind.
Okay.
Let's say that like here's what we want to do. You have like match source equals IP address right now. What if you wanted to have match like source AS equals this, right? And now you've got a packet with an IP address. Actually, what you want to have is like you effectively want to have like, does this packet have a source IP address that belongs to a set?
Yeah.
Right? So here's my question. Right? Let's suppose you want to. It doesn't seem like you have an update thing for this. Like, what I want to do is basically have a match on a set membership. Yeah. Right, where the set membership may change. Yeah. Right. So you've got changes to network, changes to the policy, and I want like to change the set.
There is a way to do this, and I'm going to pull the screen back now. I'll tell you how to do it. It may not be the most efficient way of doing it. This I'm not sure, but you can do it. The way you do it is, so we have a dynamic policy, right? There's a thing called a dynamic filter, which is a subclass of dynamic policy that, guess what, just inherits from filter as well, right? So you can create a dynamic filter that is going to change over time in response to whatever event you want, and that thing can be, say, the union of a whole bunch of matches, specific matches.
I see.
And that union, the set of matches being union can change over time as you like.
So you can define a new filter. This is what you did, right? With match URL. You did match URL.
Yeah. And so then you're just leveraging all of Pyretic's dynamic stuff already in recompilation to do that. And that's the method I preferred. I don't know if they're
so the issue I think with that is like, then like for arbitrary metadata or arbitrary sets you want to define, you have to define new functions in your language, which like kind of sucks. So
new functions,
do like match URL, now you do match AS, now you do match this, and like for every possible thing, you gotta actually change the language, which is kind of like
not change the language. I mean, you've got to write your own module. You've got to write a new module that does this thing. Now, of course, you could write a module generator that, if they all have the same form, just auto-generates them based on some parameters. But still,
Anyway,
yeah.
But I got the answer to the thing.
Okay, cool. So we got that. So now we're going to go back to classifier, and we're going to see how parallel and sequential composition on classifier entities work. Now, to review, classifier is we got rules. Rules are a match and a set of actions. We've got classifiers, which are just a list of rules. Okay? So let's look at the so we've got an invert method, which I'm going to ignore right now because it's a little less interesting. And we've got parallel composition. Okay, this is the add. So this is literally that plus that you saw in the accumulator before. And let's just work through it really quick. Add is not too bad. So what we do is we define a helper method called cross that takes 2 rules and produces their single rule output that corresponds to crossing them, like we saw in the animation from last session. So what do? Well, we take their two matches, and we get the intersection of their two matches. Great. If that intersection isn't equal to drop, no.
People just start picking up food.
Yeah, totally. Yeah. By the way, if you guys do want to start picking up food or whatever, feel free. I'm going to try to just push on to 2, at which point, yeah, we'll stop. So 11 minutes, if you're, yeah. So basically, if the intersection is not equal to drop, so there's actually a match in there, what are we going to do? Well, we're going to add we're going to take the union of both action sets. And then we're going to return a rule that matches on the intersection and has the set of actions that are the union. Otherwise, if the intersection is drop, so there's literally no intersection, we're going to return none. There's nothing here in their intersection. Okay? Now that we've defined cross, basically what we do is we create a new classifier, output classifier C3, on line 155, and we do a little assertion to make sure, things aren't crazy. And then we say, okay, for each rule in C1 rules, for each rule in C2 rules, so first rule, second rule, third rule, we're going to calculate the cross. If the cross exists, so if it's not none, we're going to append it to the classifier in the next position. And we'll just do that until we've done the full cross, at which point we'll check. Hey, if we've got nothing in the classifier, then let's just append one rule that says, if it's identity, output the empty set. Otherwise, we're going to call an optimize method on it, and then we're going to return it. So let's take a look at this optimize method.
By the way, is this all this thing comes under the evaluation part, or is it like?
No, this is compilation now.
Oh, okay.
So this is all compilation. So the way optimization works, so this is shadow optimization, and right now the way it works is remove a.
Can you remind me what that means?
So remember when we produced that top level classifier before that had 3 rules that each matched f equals v? The second and third rule could never be hit.
Right.
So this is what does that kind of detection and removal. So remove shadow covered single basically says, hey, the optimized classifier is a new classifier. For each one of these rules, what we're going to do is we're going to create an accumulator that's going to track what matches we've already seen. And then, we're going to check the rule, the current rule, and say, hey, or rather for each rule, we're going to see, for any other rule, does it cover that rule? And just throw things out, or rather selectively add things in. So the first rule we see can't have been covered by anything, so we're going to add it in. And the next rule, well, we'll see if it was covered by the first rule, and if so, we won't add it in, and so forth. So this is just, some very tight code way of expressing that.
So why do we have to cover and exact? Does cover doesn't cover also cover the exact cases as well?
Oh, so no. So exact is a little bit different than cover because we do things like what you do IP prefix matching, right? So if I give a bigger IP prefix, or you can think of it like this, like if I give you a match f equals v, right? And then I see later on another match, which is f equals v intersected with f prime equals v prime, right? Again, if I do covers on that, I'll see f equals v. Well, anything in f equals v is also in f equals v intersected with f prime equals v prime. So they don't exactly match one another, but f equals v definitely covers. So again, that's another place where covers is called. So.
Why would you need the exact?
Oh, it was just, the first thing we did, because it's obviously correct and you don't need to implement covers. No, but also if you wanted to say do a performance analysis, like how much better is the covers heuristic, because covers does require more calculation, right? So what are the trade-offs? Well, we kept it there, You can choose to use it instead or evaluate it instead. And there are other better ways of doing shadowed cover single, like keeping track of the spaces that have been covered by multiple rules in conjunction with one another. And using that. but that's even more computationally expensive and difficult to get right, so I didn't implement it. Or we haven't implemented it yet. So that's...
I think in general, performance optimization of the rule table, the compilation process, reducing how many packets go to the controller, all interesting scope to do more.
Yeah, definitely.
Like you sort of did the things that people were doing about, did the things that were sort of
obvious, easy.
Do, like knock off the first 90%
yeah,
or whatever.
Exactly. Oh, there's a lot more to do. And the dynamic compilation, I mean, the caching that we have right now is like very, very simple. I've got an idea for a whole recompilation algorithm. There's also Shin's algorithm. There's also the one that you came up with. So they're like a variety of different approaches. It'd be cool to see them compared, you know, for performance size, how actual switches react to them, etc. So, you know, there's a rich space. But what I'm going to do is I'm going to quickly knock this off in 5 minutes, and then we're going to take a break, and the folks from Europe can go to sleep. Because I know it's already getting late there. And I appreciate you guys sticking with us for so long. It's gratifying to see so many folks still hanging out. So line 74, this is the sequential that you saw in the reduce of the classifiers in the compile of sequential compilation. And how does this R shift work? Well, it's a little trickier. So the first thing over here is commute test. And basically, the logic that Jen was describing before on the board for when you figure out, hey, we've got one rule, we've got another rule, does the output actually exist? And if so, what were the changes that need to be added? So this is a test that's used to mechanically move that process forward. And I'm not going to go into the details right now because 5 minutes isn't enough time, but we can dig into that later if you'd like. But that's what commute test does, basically. And sequence actions is a way of, so the way we do this, actually, let's go to the bottom, and I'll explain it from the top down instead of the bottom up, because I think it'll be a little more intuitive that way. So we create a new classifier. So for each rule in C1's rules, again, we're going to loop over things. We're going to say, hey, if there are no actions in here, well, there's no point in doing a cross with the rest of the stuff in the list because this is a drop. So we'll just append it and move on. Otherwise, it makes sense. Otherwise, we do need to go and calculate things. So what are we going to do? For rule 2 in C2 rules, what we're going to do is we're going to do a cross between rule 1 and rule 2. And this, unlike in the previous case, is actually going to output a small classifier instead of a single rule. We'll see why momentarily. Now, if this classifier is non-empty, then what we're going to do is we're going to actually take our big classifier and we're going to append this little classifier to it. Now, the funny thing about the cross over here is when I say classifier, it's not quite a classifier. It's a classifier with its last entry stripped out, because classifiers are complete. They just express every packet's behavior. Thus, any packet that they don't have something to say useful about, they're just going to drop at the end. So this is actually a pseudo-classifier that gets produced by the cross, not a true classifier. And then after we've done all that, we optimize. So clearly the interesting thing here is in the cross method. So let's take a look at that cross method. So how does a cross with 2 rules in sequential work? Well, first we create a new classifier which starts out as none, C. Then for each one of the actions in the action list on the right, so each one of these will produce a new packet. And those packets may be changed in different ways. And they're all going to flow into the next rule. So for each action on the right-hand side, we literally might have a different rule being materialized on the output side. That's why, so to put this in different words, effectively, if you think about evaluation, packet comes in to our first class, to our first policy, a bunch of packets come out. Those bunch of packets, when at the classifier level, have been created by a single rule, because we can only get one hit in the rule. So we get a bunch of packets out. those packets themselves may match different rules in the second classifier. And because that's possible, what we need to do is we need to calculate the rule that would be output for each potential set of packets. And then we need to combine them together in parallel to make it all work right. So this is exactly what happens over here. So for each one of these actions, we're gonna take the cross of the actions. So R1 with its action that's currently being considered, and R2 with all of R2's actions. And we're going to do this for each action in R1. And then, so if C's none, C's just a cross. If C isn't none, and the cross isn't none, then here's what we're going to do. We're going to say the temporary C is our previous classifier, parallel composed with this new cross. So we're going to go through each of the actions. We're going to output a rule, or in fact a classifier, and now we're going to parallel compose all those together so we actually get them happening in parallel. Because we have different sets of packets that are going to follow different fate paths, but they only follow those fate paths simultaneously, essentially. And then we're going to do some appending of the C and the cross, and then we're going to optimize it, and eventually we're going to return it. So it's kind of a triply nested induction, basically. And the rest of this stuff up over here is going through the details, making sure every part of that is done correctly. And that's 5 minutes. So we're going to take a break. Quick questions now. We can definitely dig into the details of this more later if it's, useful. But this should give you a taste of, exactly how it works. Okay. I declare break.
I guess I just
okay.
Highlight. So
sure.
This is also targeted towards like overflow 1.0 tables. So this is like when we talked before, classifiers, long rule, what are you assuming about switches? It seems to be all in here, right? So,
yeah, it is.
So if you wanted to basically do something else like at QoS or specific kind of counter or something.
Totally, or deal with, or have multiple tables in hardware or any of that.
Right. If you want to basically like make this work with different targets, you want to basically look at the classifiers. Yeah, so you might want to create different compile methods, or one generic compile method that then takes metadata on what type of switch, what target it is, and then calls a specialized compile. There are a variety of different ways you could hook it into the code, but I think that's generally the design choice. So yeah, folks in Europe and elsewhere, thank you so much for joining. The rest of today I think will be a bit more informal, but we'll start up sessions again tomorrow morning. I'll probably do a bit more talking, and maybe we'll have some other presenters as well. Okay, so thanks for joining, everyone. And folks here, go eat your lunch.